Good morning. Okay, can I start the presentation? Hi everyone. My name is Toshiki Takeuchi from Tenku in Japan. So first, thank you for coming. I'm so happy to see so many people coming to my talk because I was afraid everyone might go the talk in the next room. So I couldn't sleep well last night. I'm glad. So let's get started. Today I will talk about sequence and concurrent processing for huge genomic data using Clojure. First, who am I? I am a researcher and software engineer at Tenku. I have been using Clojure and Clojure script to implement a practical software for over 4 years and make some Clojure libraries open source. See my GitHub if you are interested. I interned at Tenku and wrote Clojure since I am a university student. Last year, I held a PhD from the University of Tokyo. After that, I officially joined in Tenku. Well, about Tenku, as this logo shows, XCOO is pronounced as Tenku. Tenku is a Japanese startup company providing genomic intelligence solution. Our company creates services with 3 policies: intuitive design for everyone, knowledge of advanced computing, and high ability of implementation of software. Of course, we're using Clojure and Clojure script as the main programming language, also using somewhat Java and Python, little JavaScript and C++ and so on. This is outline of today's talk. First, I will introduce genomic analysis and bioinformatics. After that, I will explain the main topic of my talk, why we decided to use Clojure in bioinformatics field. In addition, I will touch on how Clojure is used in our entire solution. So before starting the contents, I'd like to know how many people who know somewhat bioinformatics. Oh, so many, more than I expected. So some bioinformatics words will appear in my slides, but you don't have to understand the detail of the word. The main topic is Clojure and our experience using Clojure for our solution. I start my talk from brief introduction of genomic analysis. Genome is genetic materials of an organism like DNA or RNA. In the case of human genome includes 3 billion letters of ATGC. So genome information is very useful for understanding organism, research for genetic disorders, and use for medical treatment. So recently, genome can be read by a machine called sequencer easily and quickly. So many research institutions in the world conduct genome analysis. Well, why did genomic analysis become so popular? Because of low cost and speed. This chart shows the change of cost needed for DNA sequencing. The green line is DNA sequencing cost, and the white line is Moore's law. So as you can see, the cost reduction is much faster than Moore's law. So, and sequencing speed is also getting faster. So in practical case, partial genome can be read in a few hours. This chart shows past and future accumulation of genomic data. Yellow line is Illumina's estimation. Illumina is one of the biggest company of biotechnology. From this chart, you can understand that genome data is rapidly accumulating, and the post-process of sequencing is serious issue. So such post-process is in bioinformatics field. So that is analyzing process of sequenced genome data. That is informatics and data analysis domain. In such bioinformatics field, we mainly use Clojure. So next, I talk about why we use Clojure and why Clojure is good at bioinformatics with actual examples. These days, genome data is led by next generation sequencer. The genome data generated by NGS is huge. The output format is different by NGS machines, but the de facto standard format is FASTQ format. FASTQ is a text-based format, including both sequence letters like ATGC and quality scores. Basically, this file is the starting point of genomic analysis. The FASTQ data size is very, very large, as much as from gigabyte to terabyte per specimen. This is one specimen size. So for example, a full genome FASTQ is 366 gigabyte data size and includes 115 gigabases. This base means one character of ATGC. So even exome sequencing, this is partial genomic data. So even it is 35 gigabyte and 21 gigabases. So performance is very important factor when handling such huge files. So in fact, most of the bioinformatics tools are developed in C or C++ or Java. It's for performance. So these tools are very popular in bioinformatics. So for example, BWA is written in C and Bote2 in C++. Some tools are in C and C++, Picard in Java. And Python is written in Python, but it is just some tool wrapper. So indeed, these tools are very fast, but we felt the code base is too complicated. Performance is important, it's true. So, but we feel simplicity is also important because algorithm or logic for analysis frequently changes in bioinformatics field. So to follow the cutting edge method and repeat trials and errors, both performance and simplicity should be realized simultaneously. So that's we decided to use Clojure. By Clojure, performance is achieved by concurrent processing and simplicity is achieved by sequence processing. So I will show details of this processing using one of our open source libraries. It's Clojure. Clojure is a DNA sequence alignment map library for Clojure. So Clojure is open source on GitHub, and its latest version is 0.5.0. And we also published an academic paper of Clojure in the academic journal, Source Code for Biology and Medicine. So part of this talk is written in the paper, so read it if you are interested. Well, I explained from sequence processing. So why is sequence processing important in genomic analysis? That is because genomic data is actually character sequence. So as many of you know, DNA and RNA consists of 4 nucleotides, ATGC, so adenine and thymine for DNA, and uracil for RNA, and guanine and cytosine. So genome data is a character sequence, including such ATGC letters. So to be accurate, sequence including a lot of segments, that is ATGC sequence, like the right figure. Because NGS machine cannot read entire genome sequence once, so NGS reads partial segments of genome sequence that is called read. So there are some red letters in the right figure. A and T and C, and they are different base from reference sequence, we can know they might be a genetic variation. So Lisp is good at list processing. So as you know, Clojure is also good at sequence processing. Especially in genomic analysis, it is because of higher order functions and lazy sequence. So higher order functions enable the sequence processing simple, intuitive, and easy to change. And lazy sequence enables processing with huge genomic files. Higher order functions are functions like map and filter. And in Clojure, threading macros are very convenient for sequence processing. It seems obvious for Clojurians, but it is truly useful for genomic analysis. So because genomic data is actually sequence data, and sequence processing, like filtering, sorting, is very common process. So the below code is an example of reading and passing some format file using Clojure. Some format is one of the formats genomic data. Some reader opens the SUM file, and some read alignments reads segments of genomic sequence from the SUM reader. So filtering by R name is very common. So if you want to get only CHR7 segments, add filter like this. CHR7 means 7th chromosome. So if you want to get only flag is 16, add this filter. So sorting by our name or position is also popular process. If we want to sort by position, add sort by pose. So these easy adding and removing such sequence functions are very important. So these quick trials and fixes are needed at practical scenes in genomic data analysis. So because basically genomic analysis is still somewhat experimental and unstable. So bioinformaticians are trying to find better filtering parameters night and day. So the combination of Clojure's sequence functions and repo accelerate this process. Another merit is lazy sequence. The most of Clojure's sequence functions return lazy seq. In genomic analysis, lazy sequence is so useful in point of memory because huge genomic data cannot be held in memory. So lazy sequence from file input, like line seq, makes sequence processing with file too simple. So like the left code, line seq returns lazy seq from reader. Similarly, the most of reading functions of Clojure also return lazy seq from large genomic files, so like the right code. So this code works on terabyte size files. This code style is quite readable and intuitive. I have introduced our library Clojure, but there is another bioinformatics library in Clojure, Clojure biosequence. It is not our library, but Clojure biosequence is a Clojure library designed to make the manipulation of biological sequence data easier. So this has a similar motivation. In README of Clojure biosequence, it is written that mechanisms for lazy processing of sequences from very large files. That is same motivation of Clojure 1. So from that, you will know Clojure lazy sequence is suited to genomic analysis. Next is about concurrent processing. Sometimes Clojure's performance becomes a hot topic. These are a few examples. A thread of why is Clojure so slow in Hacker News? Another is Clojure performance really that bad? Reddit. I think that not again. Usual answers for these questions are that Clojure has extremely good performance for dynamic language in comparison with Python or Ruby, but Clojure is much slower than C or C++. So it seems right, but I think not so. So it's not always true in practical cases. It's because concurrency. So as you know, Clojure provides very easy and strong concurrency mechanisms. So basically, Clojure has 4 types of concurrencies. The first is agent functions, including send and send off. The second is future functions. PMAP-like functions also internally use future, so PMAP, because p-values are kind of future. As other concurrency mechanisms, there are coasync and reducers. So in these features, which is appropriate for sequence processing? So for sequence processing, PMAP and reducers seem well suited. PMAP is extremely simple to change serial sequence processing to mass-threaded one. So it's just replacing map with PMAP. So, but in such cases, simple replacement may not be so good performance because of context switching. So you should remember partition role plus PMAP pattern. So that splits source sequence with a fixed chunk size and evaluate the chunks concurrently. PMAP is best in the point of simplicity, but we cannot control parallelism like the number of threads. So PMAP always use CPU plus 2 threads. So we don't use PMAP in Clojure. So about reducers. Reducers uses Java's fork join framework and has great performance. Reducers looks like good choice, but it cannot be used in our case. So there are 2 reasons for that. The first reason is the reducers fold only allows persistent vectors and maps. So in other words, all analyzing data needs to be in memory. So, but as I mentioned before, genomic data is so huge, so that cannot be held in memory. The another reason is I/O bounds. File reading becomes a bottleneck when increasing the number of threads. So if comparing the 2 ways, above way is reading file first and processing concurrently after that. And the below way is processing while reading file. So if comparing these 2 ways, just below way is faster in your case. So of course, that depends on machine specs or analysis algorithm, but we don't use reducers for these reasons. So what do we use? Currently, we use Claypool library. Claypool is not our library, but it is very convenient, so we heavily use it. Claypool provides a flexible PMAP and other parallel functions such as PMAP, pcall, p4, pdoseek. Claypool's PMAP receives a thread pool as the first argument. So we can control parallelism, like the number of threads, kinds of threads, and thread lifetime. In addition, Claypool's functions are similar to Clojure core functions, except for the first argument, so it is easy to make the sequence processing concurrent. So in the below code, CP with shutdown controls thread pool lifetime, and CP thread pool creates a new thread pool with a specified number of threads. And CPU PMAP executes the function concurrently, like Clojure core PMAP. So partition all plus PMAP pattern is also appeared. Such codes are frequently found in our Clojure source code. Then let's see actual performance and simplicity of our code. These are execution time and change number of threads. The left chart is one indexing process, and the right is one of the pile-up process. So though I not explain the detail of the process, but there are such process in genomic analysis. So we use 13.2 gigabyte size genomic data of the 1,000 genomes project and measured these on these 12 core machines. The blue line is the change of our library Clojure. The green line is SumTools 1, and the red line is Pickle 1. These versions SumTools and Pickle did not support multi-threading execution, so the time under one thread is only drawn. From these results, the execution times for Clojure are getting better until the 4 threads in indexing and 3 threads in pileup. The times for concurrent Clojure are near ones for other two. So in indexing, almost same as Pickle and twice longer than SumTools, and in pileup, 1.3 times longer than SumTools. We think these results are enough for practical use. So this measurement is at the time of our journal paper. So using somewhat old version of Clojure and other tool. So if you want to check the latest performance, try remeasuring it in Clojure project. It is probably much better than that measurement. I created a simple benchmarking framework called Libra. So for easily checking performance. So Libra provides a Clojure test-like benchmarking features like def bench, and also lining and plugging and boot tasks and optional criterion integration. So after preparing a benchmark code in bench directory, and you just input command line Libra, so it's very easy. So, okay. I think continuous benchmarking is so important to avoid performance degradation in the project, that performance is a critical issue. Well, how about simplicity? Unlike performance, it is hard to measure simplicity because it is subjective. So this is lines of code comparison between Clojure, SumTools, and Pickle. The rightmost column shows the number of effective lines. So the LOC of Clojure is about quarters that of SumTools and 1/9 that of Pickle. Of course, this result may not show actual simplicity, but we feel the code base of Clojure is more than simple. From these results in bioinformatics, we found Clojure satisfies both performance and simplicity, so that's why we decided to use Clojure. So I think performance should be considered from the viewpoint of total cost of implementation and syncing. So on that point, Clojure has a marvelous balance of them, and it is the most important. Last, I will touch on how Clojure is used for a wide range of our solution. We provide a total genomic solution called Clovis. The name of Clovis comes from chromosome and visualization. Clovis supports a full range of data analysis, including genomic, biological, medical, and clinical data. So Clovis consists of 4 modules: Clovis analysis for genomic data analysis, and Clovis database for connecting genomic information and academic knowledge, Clovis report for reporting medical results, clinicians, and expert panels, and Clovis browser for visualizing, analyzing information for researchers. So Clovis is actually used in some field, for example, in the project in the University of Tokyo. Clovis is basically a web-based product, so users can access analysis results through a web browser, for example, Genome browser with fast and seamless rendering, and knowledge search engine, and clinical report. these are all built on modern web browser. So of course, we also use Clojure in this part. For example, OM, Core Async, and so on. So now I show the demo of Clovis. It's difficult to this from this angle. Okay, I prepared the movie. This is a demo of the Clovis visualization. This is a Clovis browser demo, so one of the 4 modules. So this demo site is open to the public, so anyone can try the demo from the Clovis website. So let's try. On the top toolbar, you can choose a chromosome, position, scale, and search with gene name. And the left pane is a list of reference and genomic files. So in the main pane, histogram of genomic data, genomic segments data are shown. So we use OM and Core Async for the top toolbar or left pane. And in main pane, we use WebGL and web workers for managing local data, so for high performance rendering. Okay. This is overview of our system. So the genomic data led by NGS is split by pre-process. So and the normal ones, 2 more data pass through these 3 processes, and they are integrated, and the variant information is analyzed. So in annotation modules, annotators such as knowledge is about relation between variant and clinical information from public databases like DBSNP, CRIMBA, clinical trials, and academic journal papers database like PubMed. So and annotator add such information to variance data. And in this part, we use somewhat AI technologies like natural language processing and deep learning. Then in reporting modules, the reporter arranges those information and analyzes raw data and submits them to users. The 3 kinds of users can access these reports. So researcher can access annotated information and analyze raw data, so using for academic research. Expert panels can see the reports through website, and the clinicians can see the paper report. This is a rough data flow. So where is Clojure used in this flow? So these overlays show related libraries used in each part. Can you see? So green names are Clojure libraries. For example, AlgoGeneric and Core Async are used for quality control, and as I mentioned before, Clojure and Crypto are used for sort, indexing, deduplication, and realignment process, and Crypto also used a variant core process. And in the annotation module, annotator use REST API to communicate to knowledge search engines. So annotator uses CLJ HTTP, and knowledge search engine uses Ling or Baidi, or so providing a REST API server. And using Java JDBC, SQL, runtime for managing MySQL, and Clojure and Dynet to use AI technologies. Dynet is Python libraries. In reporting modules, reporter uses BID, Clojure script, OM, Savron, and Pushy for rendering web reports. And our original data store, fast data store for raw data is also use core cache, data codec, Cheshire, and Subray, like this. Like this, we use Clojure and Clojure script everywhere in our solution. So, by the way, this is my abstract. So, according to my abstract, 90% of our solution is written in Clojure. 90% is very high. So some of you may fear it is overstatement. He says maybe lie. So I think so too. But to tell the truth, it is overstatement. I regret. This is real statistics. This shows LOC distribution of programming language, which does not include comment lines and white lines. So Clojure and Clojure script code accounts for 80% of our solution. So I'm afraid that it is less than 99%. Java accounts for 12% and Python for 7%. That is because we use Java for some low-level I/O and Python for AI-related codes. So, but 90% I said is not altogether lie. So, because we feel 90% is Clojure, because Clojure code tends to be short for S expression and high-level core features. So S expression makes code definition, code direction somewhat horizontal, so lines is short. So besides, Clojure core features are very high level and abstract, so it's easy to express logic with short code. Okay, I summarize my talk. As I Clojure pros for genomic analysis, both simplicity and performance are realized by features of sequence processing and concurrent processing. This enables us to concentrate and accelerate essential logic. So another pros is that Clojure script, and the ecosystem are very general. So our solution, Clovis, uses Clojure everywhere, from analysis modules on the backend and to the visualization on the web front end. So about cons, I have not so talked about weak points of Clojure, but from our experience, I feel Clojure is not so good at some domains. So the first is low-level I/O. So as I mentioned, some process are I/O bounds. So there is a limit to improvement by concurrent processing. So we use pure Java for such parts. For example, we load BGZF4J library in pure Java. BGZF is a blocked music format which is commonly used in bioinformatics. And another weak domain is AI-related domains such as natural language processing and machine learning or deep learning. So today, Python is a major interface of these technologies, and we actually use Python libraries. But I had great talks about AI in this Clojure Conje, so about Cortex, deep learning 4J, and so on. So I feel these domains of Clojure are getting better. So we might change our AI-related code with using Clojure. So if so, in the near future, truly 90% of our system might be written in Clojure. That is all. Thank you for listening.